One day the stars will go dark, space will grow silent, and the universe itself will begin to die. The only question left is how it happens, and whether it comes slowly or all at once. Before we dive into this topic, make sure to subscribe and comment where in the world you're watching from. For most of human history, we've been obsessed with beginnings. Where did we come from? How did the universe start? What lit the first spark of existence? Religions, myths, and eventually science all tried to answer that one overwhelming question. The Big Bang gave us a compelling story for the birth of everything, a moment when space, time, energy, and matter exploded into existence. And for a long time, that felt like the ultimate mystery. But as strange as it sounds, there's a question even more unsettling than how the universe began. It's the question we rarely want to face. How does it all end? The end of the universe isn't just a distant curiosity, it's the final chapter of reality itself. Every star, every galaxy, every atom, every thought that has ever occurred is heading towards some ultimate fate. And unlike ancient myths that imagined the cosmos as eternal or endlessly repeating, modern science tells us something far more uncomfortable. The universe has a timeline, it has a past, a present, and a future. And that future is not infinite in the way we once imagined. For centuries, this question was impossible to answer scientifically. We simply didn't have the tools. We couldn't see far enough into space, we couldn't measure cosmic expansion accurately, and we didn't understand the forces shaping the universe on the largest scales. Cosmology was philosophy dressed up as science. People could speculate, but they couldn't test their ideas. Asking how the universe would end was like trying to predict the death of a star before we even understood how stars worked. That changed in the last few decades, and it changed dramatically. Today, cosmology is no longer guesswork. It's precision science. We can measure the expansion of the universe down to incredible accuracy. We can see galaxies billions of light years away, meaning we are literally looking back in time. We can detect faint echoes of the Big Bang itself, frozen into the cosmic microwave background. For the first time, we're not just telling stories about the universe, we're reading its data. And perhaps the most shocking discovery of all is this: the universe isn't slowing down, it's speeding up. Against everything physicists expected, cosmic expansion is accelerating, driven by a mysterious force we call dark energy. This single discovery transformed the question of the universe's end from speculation into something urgent, mathematical, and deeply unsettling. Once you know how fast the universe is expanding and why, you can begin to extrapolate forward. You can run the cosmic clock ahead billions or even trillions of years and see what happens. That's why modern cosmology can finally tackle the ultimate question with confidence. We now understand stars well enough to know how they die. We understand galaxies well enough to know how they drift apart. We understand thermodynamics well enough to know what happens to energy over long stretches of time. And we understand gravity and quantum physics well enough to glimpse the final acts of reality itself. This isn't science fiction. This isn't philosophy. This is physics following its own equations to their inevitable conclusions. And what those conclusions suggest is both awe-inspiring and terrifying. The universe is not heading toward a dramatic finale filled with explosions and fire. Or maybe it is. Or maybe it ends quietly, fading into darkness, so complete that time itself loses meaning. The truth is, science has narrowed the possibilities, and none of them look comforting. For the first time in history, we are a species capable of asking not just where everything came from, but where everything is going. And once you ask that question, you can't unask it, because the answer doesn't just tell us about the universe, it tells us something deeply personal about our place in it, how fragile everything is, and how precious this brief moment of light and structure truly is before the cosmos writes its final line. For most of the 20th century, scientists believed they already knew how the story would unfold. The universe began with the Big Bang. Matter flew outward, gravity slowly pulled everything back, and one day the expansion would grind to a halt. It was an elegant idea. Expansion versus gravity, a cosmic tug-of-war that would eventually end in balance or collapse. The only real question, they thought, was whether there was enough matter in the universe to stop the expansion and reverse it. In other words, would the universe slow down gently or slam into a catastrophic big crunch? Then, in the late 1990s, the universe pulled the rug out from under us. Astronomers were studying distant supernovae, exploding stars so bright they can outshine entire galaxies. These stellar explosions act like cosmic mile markers. Because we understand how bright they truly are, we can measure how far away they are by how dim they appear. When scientists began comparing the distances of these supernovae with how fast their galaxies were moving away, they expected to confirm that expansion was slowing down. Instead, they found something that made no sense at all. The universe wasn't slowing down, it was speeding up. This discovery was so shocking that many scientists initially assumed it had to be wrong. Instruments were recalibrated, data was checked and rechecked. Independent teams ran the same measurements using different telescopes and methods, but the result refused to go away. The farther back in time they looked, the slower the expansion had been, which meant that at some point the universe had flipped a switch. Expansion wasn't losing energy, it was gaining it. This single observation shattered decades of assumptions and forced physicists to confront an uncomfortable reality. Something unknown was pushing the universe apart. They called it dark energy, not because it's evil or mysterious in a poetic sense, but because we have no idea what it actually is. We can't see it, we can't touch it, we can't measure it directly. We only know it exists because of what it does, and what it does is overpower gravity on the largest scales imaginable. Dark energy changed everything. It didn't just add a new ingredient to the universe, it completely rewrote the recipe. Instead of matter and gravity dominating cosmic evolution, dark energy turned out to be the main driver of the universe's future. Today, we believe it makes up roughly 70% of everything that exists. Not atoms, not stars, not galaxies, something else entirely. The implications were staggering. If expansion is accelerating, then galaxies will drift farther and farther apart, faster and faster, until eventually they disappear beyond our observable horizon. Light from distant stars will never reach us, the night sky will go dark, the universe will grow colder, emptier, and more isolated with every passing billion years. And suddenly, the idea of a collapsing universe looked less and less likely. Gravity, it turned out, was losing. No matter how much matter clumped together, dark energy was winning the long game. This discovery didn't just shock cosmologists, it introduced a deep existential discomfort. If the universe is accelerating forever, then there is no grand return, no cosmic reset, no rebirth waiting at the end. There is only expansion, thinning reality, until structure itself can no longer survive. The accelerating universe forced humanity to confront a brutal truth. The cosmos is not designed for permanence. It is not moving toward balance or stability. It is racing toward an unknown future driven by a force we barely understand. And once you accept that, the question of how the universe ends becomes unavoidable, because acceleration doesn't just change the speed of expansion. It determines the final fate of everything that has ever existed. If the universe has a most likely ending, this is it. Not an explosion, not a collapse, not a dramatic final moment of fire and noise, just silence, darkness, and an emptiness so complete that it's almost impossible to imagine. Scientists call it the Big Freeze, or heat death, and despite how understated the name sounds, it is one of the most haunting ideas modern cosmology has ever produced. The Big Freeze begins with a simple fact: the universe is expanding, and that expansion is accelerating. As space stretches, galaxies move farther apart. Over time, gravity loses its grip across vast distances. Galaxies that were once neighbors drift beyond each other's reach, pulled apart by the relentless expansion of space itself. Eventually, every galaxy becomes an island, isolated in an ocean of nothing. At first, the universe still looks alive, stars continue to shine, planets continue to orbit, but the clock is ticking. Stars are not eternal. They burn by fusing hydrogen into helium, releasing energy in the process. And hydrogen, the fuel of stars, is finite. Over trillions of years, stars exhaust their fuel one by one. Massive stars explode. Smaller stars fade quietly into cold, dim remnants called white dwarfs. New stars stop forming because the raw material needed to create them has been used up or scattered too thinly across expanding space. Eventually, the universe enters what physicists call the stellar graveyard era. No new stars ignite. Existing ones slowly die. Galaxies grow dark. The night sky, if anyone was still around to look up, would be completely black. No glowing points, no distant suns, just darkness, but the freeze doesn't stop there. As time stretches toward incomprehensible scales, billions, trillions, then quadrillions of years, even the remnants of stars begin to decay. White dwarfs cool until they become black dwarfs, objects so cold they emit virtually no energy. Neutron stars slowly lose their heat. Black holes, the most extreme objects in the universe, begin their own slow death through Hawking radiation, leaking energy over unimaginable time spans until they evaporate entirely. What remains is a universe approaching perfect thermodynamic equilibrium. Energy is spread so evenly that no useful work can ever be done again. No motion, no change, no process is capable of creating structure or complexity. Time still exists, but nothing happens within it. This is what physicists mean by heat death. Not heat in the sense of fire, but the absence of temperature differences, the absence of gradients, the absence of anything that allows events to occur. A universe where entropy has won completely. Galaxies drifting apart forever means that even the concept of a shared universe disappears. Each region of space becomes causally disconnected from all others. Communication becomes impossible. Movement becomes meaningless. The cosmos turns into an endless frozen void. There is something deeply unsettling about this ending, not because it's violent, but because it's indifferent. The universe doesn't rage against existence, it simply lets it fade away, slowly, quietly, irreversibly. The big freeze tells us that the universe doesn't end with a bang, but with a whisper, and that whisper stretches on forever, long after the last star has gone dark, leaving behind a reality where emptiness itself is the final state of everything. The big freeze is unsettling because it is quiet. The big rip, on the other hand, is terrifying because it is violent. It is the cosmic ending that doesn't wait patiently for stars to fade, but instead tears the universe apart piece by piece, right down to its most fundamental structure. And disturbingly, it's not science fiction. It is a real possibility allowed by modern cosmology. The Big Rip begins with a simple but frightening assumption. What if dark energy doesn't stay constant? What if it grows stronger over time? Right now, dark energy is already overpowering gravity on the largest scales, forcing galaxies apart faster and faster. But in some models, dark energy isn't a gentle background force. It's something called phantom energy, a form of energy that increases as the universe expands. If that's true, then expansion doesn't just accelerate, it runs away. At first, nothing looks wrong. Galaxies drift apart faster than before, but gravity still holds individual galaxies together. Then, at a certain point in the future, dark energy becomes strong enough to overcome even that. Entire galaxies are pulled apart. Stars that once orbited peacefully are ripped away from their galactic cores, flung into the void, as isolated suns racing through empty space. Then it gets worse. As dark energy continues to intensify, it starts attacking smaller and smaller structures. Solar systems no longer survive, planets are torn from their orbits. Gravity, the force that has shaped the universe since the beginning of time, simply loses. Earth, if it still exists, would be ripped away from the sun as space itself stretches between them faster than light can cross the gap. And then comes the truly horrifying part. Dark energy doesn't stop at stars or planets. It keeps growing. Eventually, it becomes strong enough to overcome the forces that hold matter itself together. Molecules are torn apart. Atoms are shredded as the electromagnetic force can no longer resist the expansion of space. Even atomic nuclei, held together by the strong nuclear force, are ripped apart. In the final moments of a Big Rip universe, there are no objects left, no particles, no structure. Space-time itself is stretched beyond recognition. The very concept of distance loses meaning because every point in space is being violently pulled away from every other point. Reality doesn't freeze, it disintegrates. What makes the Big Rip so disturbing is how precise it is. Physicists can actually calculate a timeline. In some models, the destruction happens in stages with a countdown. Billions of years before the end, galaxies vanish. Millions of years before the end, stars are destroyed. Minutes before the end, planets fall apart. Fractions of a second before the end, atoms cease to exist. There is no aftermath, no quiet void, no lingering darkness. The universe doesn't survive its own expansion. Whether the Big Rip will happen depends entirely on the true nature of dark energy, something we still don't understand. Current observations suggest dark energy behaves like a constant, which favors the big freeze, but the margin of uncertainty remains. And within that uncertainty lies one of the most violent endings imaginable. The Big Rip is a reminder that the universe is not just indifferent. Under the wrong conditions, it is actively hostile to structure, order, and existence itself. If dark energy grows unchecked, the universe doesn't fade away. It destroys itself from the inside out. Long before dark energy entered the conversation, the universe was expected to meet a very different fate. Not one of endless expansion or violent disintegration, but collapse. The Big Crunch was once the dominant vision of how everything ends, a universe that expands, slows down, stops, and then reverses, falling back in on itself under the relentless pull of gravity. It was cosmic symmetry at its finest, a beginning in fire and end in fire. The universe born in a Big Bang, dying in a Big Crunch. The idea came directly from gravity's nature. Gravity pulls. It clumps matter together. It builds stars, galaxies, and clusters of galaxies. For decades, physicists assumed that if there was enough matter in the universe, gravity would eventually win. Expansion would slow, galaxies would begin to drift back toward one another, and the universe would start contracting. Temperatures would rise, densities would increase, space itself would shrink. In the final stages of a Big Crunch, the universe would become hotter and more chaotic. Galaxies would collide constantly. Stars would be crushed together. Matter would be compressed into an ever smaller volume until, in the final moment, all space, time, and matter would collapse into a singularity, perhaps giving birth to another Big Bang. Some even imagined an eternal cycle. Bang, expansion, crunch, rebirth, a universe endlessly recycling itself. It was a comforting idea in a strange way, an ending that led to a new beginning. But then the observations came in. When astronomers measured the total amount of matter in the universe, normal matter, dark matter, everything, they found a problem. There simply wasn't enough gravity. Even when accounting for dark matter, gravity fell short of what would be required to halt expansion. And when the discovery of dark energy arrived, accelerating the expansion instead of slowing it, the Big Crunch lost most of its footing. If dark energy continues to push space apart, gravity never gets the chance to reverse the motion. The universe doesn't collapse, it escapes. And yet, the Big Crunch is not completely dead. There is still uncertainty surrounding dark energy. We don't know if it is truly constant. We don't know if it could weaken over time, change behavior, or even reverse. If dark energy were to decay or disappear far in the future, gravity could regain control. Expansion could slow, then stop, then reverse. The universe could still collapse. There are also speculative ideas involving higher dimensions, unknown fields, or modifications of gravity itself that could alter the universe's long-term fate. Physics at cosmic scales is still incomplete. What we know today may not be the final word. The Big Crunch remains a reminder of how fragile our conclusions are. A single discovery can rewrite the future of everything. It also highlights something profound. The universe's fate hinges on a delicate balance between forces we barely understand. Whether the universe freezes, rips apart, or collapses back into itself depends on numbers we're still measuring and laws we're still uncovering. The Big Crunch may no longer be the favorite ending, but it lingers as a possibility, waiting for gravity to have the final say. There is an ending far more unsettling than freezing or ripping apart, because it offers no warning, no build-up, no slow fade into darkness. One moment the universe exists exactly as it does now, the next moment it doesn't. This is the idea of false vacuum decay, and it may be the most terrifying possibility modern physics has ever uncovered. To understand it, you have to let go of the idea that the universe is truly stable. According to quantum field theory, everything in the universe exists in energy states. Some are stable, others are only apparently stable. A false vacuum is one of these deceptive states. It looks calm, it looks permanent, but underneath it's unstable, like a ball resting in a shallow dip rather than the lowest possible valley. The universe may feel solid, predictable, permanent, but it could be balanced on the edge of a deeper, more stable state we haven't fallen into yet. And if that's true, the fall could happen at any time. False vacuum decay wouldn't begin with collapsing galaxies or dying stars. It wouldn't announce itself with explosions or gravitational waves. It would start with a microscopic quantum event, a random fluctuation, a tiny region of space tunneling into a lower energy state. Something so small it would go completely unnoticed until it wasn't small anymore. Once that transition happens, it creates a bubble of true vacuum. Inside this bubble, the laws of physics are different. The values of fundamental constants change. Forces behave differently. Particles may no longer exist as we know them. Chemistry, atoms, stars, even space-time itself may be impossible, and this bubble expands, not slowly, not gradually, at the speed of light. That's what makes false vacuum decay so absolute. The bubble doesn't push through space, it replaces it. Every point it touches is rewritten instantly. There is no shockwave you could outrun, no signal you could detect in advance, no warning, ever. By the time you became aware of it, you would already be gone. One moment, Earth orbits the Sun. The next moment, the laws that allow atoms to exist are gone. Matter dissolves, space collapses into something unrecognizable. Cause and effect end. What's especially disturbing is that this scenario doesn't require the universe to grow old. It doesn't wait for entropy. It doesn't care about expansion or gravity. It could happen tomorrow, or a trillion years from now, or it may never happen at all. Quantum mechanics only gives probabilities, not schedules. Even more unsettling is that our universe appears suspiciously close to this kind of instability. Measurements of the Higgs boson suggest that our current vacuum state may be metastable, not guaranteed to decay, but not guaranteed to last forever either. We may be living in a universe that is technically temporary, held together by cosmic luck. False vacuum decay represents a kind of existential humility. No final chapter, no grand ending, no cosmic dignity, just instant erasure. And if that sounds unfair, that's because it is. The universe owes us no warning, no explanation, no closure. It simply obeys the laws of quantum mechanics, even when those laws allow for endings that are sudden, silent, and absolute. If the big freeze is a slow death and the big rip is violent destruction, false vacuum decay is something else entirely. It is cosmic oblivion, faster than fear, faster than thought, faster than the universe itself can react. And the most unsettling part, if it happens, no one will ever know it did. Black holes feel eternal. They are the most extreme objects the universe has ever created. Regions where gravity is so powerful that not even light can escape. For decades, physicists believed black holes were the ultimate cosmic survivors, the final structures left standing expanding long after stars burned out and galaxies dissolved. If anything could outlast the universe itself, it would be black holes, but even they are not immortal. In the far future of the universe, after the last stars have died and galaxies have drifted beyond each other's horizons, black holes become the dominant objects left behind. Stellar mass black holes linger where stars once lived. Supermassive black holes remain at the centers of dead galaxies, surrounded by nothing but darkness. For unimaginably long periods of time, they appear unchanged, silently orbiting an empty cosmos. Then quantum mechanics enters the story. In the 1970s, Stephen Hawking made a discovery that fundamentally changed how we understand black holes. Using quantum field theory, he showed that black holes are not perfectly black. At their event horizons, quantum fluctuations cause pairs of particles to pop into existence. Normally, these particles annihilate each other almost instantly, but near the event horizon, one particle can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This is Hawking radiation. The energy for this radiation comes from the black hole itself, which means the black hole slowly loses mass. Not quickly, not dramatically. For a stellar mass black hole, the process takes longer than the current age of the universe by an absurd margin. For supermassive black holes, it takes far longer still. Timescales measured in numbers so large they almost lose meaning. But given enough time, Hawking radiation does its work. Black holes shrink. They grow hotter as they lose mass. And eventually, after trillions upon trillions of years, they evaporate completely in a final burst of energy. No collapse. No singularity tearing the universe apart. Just disappearance. This realization is deeply unsettling because it removes the last illusion of permanence. Black holes were once thought to be the final vaults of reality, places where information and matter were locked away forever. Now we know they fade too. Nothing is exempt from the long erosion of time and entropy. As black holes evaporate, the universe enters its most barren phase. No stars, no galaxies, no planets, just a thin bath of low-energy radiation drifting through an ever-expanding space. Events become so rare that time itself feels meaningless. Nothing changes, nothing happens. This is the slow fade of reality. What's remarkable is that black holes, once symbols of destruction, become agents of cosmic closure. They don't end the universe violently. They quietly release the last stored energy, smoothing reality toward its final equilibrium. In a sense, they are the universe's way of cleaning up after itself. The death of black holes marks the true end of structure. After they're gone, there are no complex objects left, no gravity wells, no engines of motion. The universe doesn't end with a scream or a collapse, but with the final evaporation of its most stubborn survivors. Black holes remind us of something uncomfortable but profound. Even the most extreme, most powerful objects are temporary. Given enough time, everything fades, and in the end, the universe doesn't just grow cold and dark, it becomes almost indistinguishable from nothing at all. There is a future so distant and so empty that it barely deserves to be called a universe anymore, not because space disappears, not because time stops, but because nothing meaningful happens within it. Time continues to tick forward, second after second, year after year, but there are no events left to mark its passage. This is time without events, and it may be the quietest ending imaginable. In this future, the last stars have long since burned out. The final black holes have evaporated. No new light is created anywhere. Space is vast, dark, and nearly uniform. The universe hasn't collapsed or torn itself apart. It simply exists in a state of near-perfect stillness. Temperature differences have vanished. Energy is spread evenly across space. Entropy has reached its maximum. From a physical standpoint, time still exists because the laws of physics still exist. Equations still work. Space-time still has structure. But without change, time loses its meaning. Time is defined by motion, by transformation, by cause and effect. When nothing changes, time becomes an abstract parameter with no observable consequence. Imagine a clock in this universe. It keeps ticking, but nothing ever responds to it. No processes speed up or slow down. No reactions occur. No systems evolve. The ticking is meaningless because there is nothing to measure against it. This is the final consequence of entropy. The universe doesn't die in a dramatic sense. It reaches a state where it can no longer do anything. No work can be performed. No structure can form. No complexity can emerge. Even randomness becomes irrelevant because there are no systems left to be randomized. What's especially unsettling is that this future isn't chaotic. It's orderly. Too orderly. Every region of space looks nearly identical to every other region. No galaxies, no stars, no planets, no observers, just thin, cold radiation stretched across an ever-expanding void. Light still exists in principle, but it's so diluted that it's practically non-existent. Photons drift endlessly, wavelengths stretched until they carry almost no energy at all. The universe becomes transparent and silent. There is nothing to see because there is no contrast, nothing to hear because there are no vibrations, nothing to feel because there is no interaction. In this universe, even the concept of location becomes meaningless. With no landmarks, no structures, no reference points, here and there lose distinction. Space becomes an infinite sameness, a featureless backdrop with no story left to tell. This is perhaps the most haunting realization. The universe doesn't just end life, it ends narrative. There is no beginning, middle, or end anymore. No cause leads to an effect. No event follows another. Reality continues, but without experience, without observers, without memory. Time without events is not an explosion or a collapse. It is the ultimate silence, a universe that has reached equilibrium so complete that existence itself becomes static, not frozen in ice, but frozen in meaning. And once the universe reaches this state, there is no coming back. No spark remains to restart the cosmic story, no fluctuation large enough to matter. Time marches on forever, but nothing walks with it. This is what it means for a universe to truly end, not by disappearing, but by becoming incapable of change. When faced with the end of everything, a question naturally emerges, one that is as much philosophical as it is scientific. If the universe is dying, can intelligence survive it? Or is consciousness just a temporary spark destined to fade along with the stars that created it? At first glance, the answer seems brutally simple. Intelligence depends on energy. It requires gradients, structure, and change. Brains think because chemical reactions occur. Computers compute because electrons move. Civilizations exist because stars provide usable energy. When the universe runs out of these resources, intelligence appears to have nowhere to stand. But physicists are not satisfied with simple answers. Some have asked whether sufficiently advanced civilizations could stretch survival across cosmic timescales by adapting to an ever-cooling universe. As energy becomes scarcer, computation could slow down. Thought itself could be spread across longer and longer intervals. A single conscious moment might take 1,000,000 years, then 1,000,000,000, then longer still. Subjectively, intelligence might persist even as objective time races toward infinity. Others have proposed harvesting energy from the most extreme remnants of the universe. Black holes, before they evaporate, could serve as power sources. Hawking radiation, though weak, lasts for astonishing lengths of time. A civilization capable of engineering at this scale might survive long after stars are gone, feeding off the final embers of cosmic structure. Then there are ideas that push beyond survival and into escape. Some physicists speculate that intelligence could leave the universe altogether, or at least leave its current phase. If our universe is part of a larger multiverse, perhaps advanced beings could tunnel into new regions of space-time with fresh energy and lower entropy. Others imagine creating artificial universes, birthing new space-times inside controlled environments, carrying information and consciousness forward like cosmic seeds. There are even more radical ideas. Intelligence might abandon physical form entirely, existing as patterns of information embedded in quantum fields or mathematical structures. If reality itself is fundamentally informational, perhaps consciousness could persist without matter, without stars, without time, as we understand it. But every one of these ideas comes with brutal uncertainty. We don't know if such such feats are physically possible. We don't know if consciousness can exist without traditional energy flows. We don't know whether the universe allows escape hatches or resets. And perhaps most unsettling of all, we don't know whether intelligence is meant to survive at all. It's possible that intelligence is not a permanent feature of the cosmos, but a brief phase, a flicker of awareness that arises when conditions are right, asks questions about its own end, and then disappears. From the universe's perspective, intelligence may be no more significant than a spark from a dying star. And yet, the fact that we can even ask these questions matters. Intelligence may not defeat cosmic death, but it can understand it. It can map it. It can find meaning in a universe that offers none by default. Even if consciousness cannot outlast the universe, it can witness it, reflect on it, and perhaps that is its role, not to survive forever, but to know. Whether intelligence escapes the end or vanishes with it remains unknown, but the act of asking may be the universe briefly becoming aware of itself before the lights go out. Knowing how the universe ends changes something fundamental about how we see ourselves. It strips away comforting illusions and forces us to confront a truth that's easy to avoid in daily life. Nothing lasts forever. Not civilizations, not planets, not stars, not even space and time themselves. And once you truly understand that, the present moment takes on a different weight. In a dying universe, meaning doesn't come from permanence. It comes from fragility. For most of human history, people believed the cosmos was eternal and unchanging. The stars were fixed, the heavens were timeless. Human life felt small but stable within that grand order. Modern cosmology shattered that picture. We now know the universe has a beginning and it will have an end. Everything we see is temporary, suspended between two unknowable boundaries. That realization can feel unsettling, even nihilistic. If the universe will eventually freeze, rip apart, collapse, or vanish in a quantum blink, then what does anything matter? Why build, love, explore, or create if it all disappears? But that question misses something crucial. Meaning doesn't require infinity. In fact, infinity often drains meaning away. A moment matters precisely because it doesn't last. A life matters because it ends. A civilization matters because it is rare and temporary in a universe that is mostly dark, empty, and silent. Understanding the universe's fate doesn't diminish human existence, it sharpens it. We are living in an extraordinary era. Stars still shine, energy still flows, complexity still exists. Consciousness has emerged during a brief window where the universe allows it. We are not guaranteed this moment. The vast majority of cosmic time lies ahead in darkness, long after the last thought has been thought. And yet, here we are, aware, questioning, capable of wonder. That makes now incredibly precious. A dying universe also reframes responsibility. If intelligence and meaning are temporary, then preserving them matters. Knowledge, art, compassion, curiosity, these are not trivial side effects of evolution. They are rare phenomena in an indifferent cosmos. And if they vanish, the universe doesn't mourn them. Only we can. Understanding the end also humbles us. We are not the center of creation. We are not permanent. But we are participants in something vast and mysterious. The universe doesn't owe us survival, but it has given us the chance to understand it, and that may be the most remarkable gift of all. The end of the universe reminds us that progress isn't guaranteed, that time is limited, and that meaning is something we create, not something waiting for us at the finish line. There is no cosmic scoreboard, no final judgment written into the stars, only the present moment, alive with possibility. In the face of cosmic death, the most human response isn't despair, it's purpose, to learn, to explore, to care, to leave traces of understanding behind. Even if they fade someday, the universe will end. That is almost certain. But right now, it hasn't. And while it exists, while we exist, the story is still being written. And that makes this moment, not the end, the most important one of all. And when you step back and look at it all, the end of the universe isn't just a distant scientific prediction, it's a mirror held up to our own existence. Everything fades, everything changes, but right now we are here, thinking, questioning, and trying to understand a universe that will one day fall silent. That alone makes this moment extraordinary. If this journey through the fate of the universe made you think a little deeper, make sure to like the video, subscribe for more science stories that challenge how you see reality, and share your thoughts in the comments. How do you think the universe will end?